Welcome to DAR Tutors. Today, we're going to explore some fundamental applications of vectors, a key topic in the IB Mathematics Applications and Interpretation higher level curriculum. In this video, you will learn to solve three types of problems involving lines and points. First, how to find the shortest distance from a point to a line. Second, how to find the shortest distance between two moving objects. And third, how to find the intersection of lines, whether in 2 or 3 dimensions. By the end of this session, you'll be equipped with the techniques to tackle these common vector problems. Let's begin with our first objective, finding the shortest distance from a point to a line. Imagine a ship sailing in a straight path, which we can model as a line. There's a port nearby, which we can represent as a single point. The ship's crew wants to know how close they will get to the port. Visualizing this, the shortest path from the port to the line of the ship's journey is not just any connecting segment. The shortest distance is always found along the line segment that is perpendicular to the ship's path. We call the point where this perpendicular segment touches the line the foot of the perpendicular. So, to find the shortest distance, our strategy will be to find the foot of the perpendicular. Once we have the coordinates of this foot, say point R, we can simply calculate the distance between our original point P and point R. Let's formalize this with vectors. This method works for both 2D and 3D. First, we need the vector equation of our line. A line is defined by a point on the line, which we'll call A, and a direction vector, which we'll call B. So the position vector of any point R on the line is given by a scalar parameter lambda times B. Now, let's consider our point P with a position vector P. Our goal is to find the point R on the line L such that the vector PR is perpendicular to the direction vector of the line B. In other words, we are looking for the foot of the perpendicular. In vector algebra, the condition for two vectors to be perpendicular is that their dot product is 0. So, our main equation to solve is the vector PR dot vector B equals 0. Let's expand PR. PR is the position vector of R minus the position vector of P, so that's RR minus P. Substituting the equation for the line, RR, we get that PR equals A plus lambda B minus P. This gives us a plus lambda B minus P dot B equals 0. We can then rearrange this to find lambda dot B equals P minus A dot B. Once we solve this equation for the parameter lambda, we can find the exact coordinates of point R. Then the distance is simply the magnitude of the vector PR. Let's apply this method to an example. A line has the vector equation R equals the vector 1, 2 plus t times the vector 3, negative 1. We need to find the shortest distance from the point P with coordinates 5, negative 1 to this line. First, let's identify the key components of our line. The point A on the line is 1, 2, and the direction vector B is 3, negative 1. So our point A has coordinates 1, 2, and our direction vector B is 3, 1. Next, let's represent the point P as a position vector P. The position vector for P is 5, negative 1. Now, let's write the position vector of a general point R on the line. Its coordinates are 1 plus 3t and 2 minus t. So the position vector is this column vector. A general point R on the line has coordinates 1 plus 3t and 2 minus t. Our next step is to find the vector PR. We do this by subtracting the coordinates of P from the coordinates of R. PR equals the coordinates of R minus the coordinates of P. That gives us 1 plus 3 to 5 for the x component and 2 to t-1 for the y component. Simplifying, we get that the vector PR is 3t, 4, 3t. Now we apply the perpendicularity condition. PR dot B must be 0. We dot our vector PR with the direction vector B, which is 3, 1, and set the result to 0. Performing the dot product, we multiply the x components and add the product of the y components. This gives us 3 times 3t minus 4 plus negative 1 times 3 minus t equals 0. This is an equation we can solve for t. Let's simplify and solve. 9t plus t is 10t. Negative 12 minus 3 is negative 15. So we have 10t equals 15, which means t equals 15 over 10, or 3 over 2. This is the parameter value that locates the foot of the perpendicular. Now we can find the vector PR. We substitute t equals 3 halves back into our expression for PR. PR is 3 times 3 halves minus 4 for the x component, and 3 minus 3 halves for the y component. 9 halves minus 4 is 1 half, and 3 minus 3 halves is also 3 halves. So the vector PR is 1 half 3 halves. Finally, the shortest distance is the magnitude of this vector. The magnitude of PR is the square root of the square of its components. That's the square root of 1/4 plus 9/4, which is the square root of 10/4. Simplifying, we get the square root of 10 divided by 2. This is our shortest distance. Sometimes, you may only need the distance and not the foot of the perpendicular. For problems in 3 dimensions, a more direct formula exists using the cross product. The formula for the shortest distance, or the perpendicular distance d, is the magnitude of the cross product of the vector AP and the direction vector b, all divided by the magnitude of b. Here, A is the position vector of any known point on the line, and P is the position vector of the point not on the line. So AP is just P minus A. This formula essentially calculates the area of the parallelogram formed by vectors AP and B, and then divides it by the length of the base, which gives the perpendicular height. Let's redo our previous 2D example using this cross-product formula, assuming the line and point are in the xy plane where zeta. This will help us practice 3D calculations. Our line is r equals 1, 2, 0, plus t times 3, negative 1, 0, and our point is p at 5, negative 1, 0. The point A on the line can be found by setting t 0, so A is at 1, 2, 0. The direction vector B is 3, 1, 0. We have our point on the line, our point in space, and our direction vector. Now we need the vector AP. AP is P minus A, which gives us 4, 3, 0. Next, we compute the cross product of AP and B. Using the determinant method, we calculate AP cross B. The I component is 0. The J component is 0. The K component is 4 times negative 1 minus negative 3 times 3, which is negative 4 plus 9, or 5. So our cross-product vector is 0, 0, 5. Now we find its magnitude and the magnitude of B. The magnitude of AP cross B is the square root of 5 squared, which is 5. The magnitude of B is the square root of 3 squared plus negative 1 squared, which is the square root of 10. Finally, we apply the formula. The distance d is 5 divided by the square root of 10. We can rationalize the denominator by multiplying the numerator and denominator by the square root of 10, which gives 5 root 10 over 10, and simplifies to the square root of 10 over 2. As you can see, this matches our previous result. This method is a powerful shortcut, especially in 3D, when only the distance is required. However, if you need the coordinates of the foot of the perpendicular, the dot product method is necessary. Now let's move to our second objective, finding the shortest distance between 2 objects that are moving with constant velocity. This is a dynamic problem. We'll have a formula for the distance as a function of time, and then we'll find the minimum value of that function. We can think of 2 cyclists moving on a straight road. For 2 objects, let's say A and B, we need their position vectors at any time t. Each object will have an initial position, a 0 and b0, and a velocity vector, va and vb. So their positions are linear functions of time. The first step is to find the vector connecting the 2 objects at time t. We'll call this vector d of t. It's the position vector of b minus the position vector of a. Substituting the equations for RA and RAB, we get b0 minus a0 plus t times vb minus va. This vector dt represents the relative position of the objects. The term b=co is the initial position of b relative to a, and veb, vea, is the velocity of b relative to a. The distance between the objects at time t is simply the magnitude of this vector, dt. The distance, capital D, is the magnitude of the vector d of t. It will be the square root of a quadratic expression in terms of t. Finding the minimum of a square root function can be tricky. Here's a simplification. The distance d will be at its minimum when its square, d squared, is also at its minimum. So instead of minimizing the distance d, we can minimize the square of the distance, d squared. The formula for d squared is the dot product of the vector d of t with itself. This results in a simple quadratic function in t. Once we have this quadratic, we can find its minimum using calculus by setting the derivative to 0. A simpler method, especially for those in AI/HL, is to use the formula for the vertex of a parabola. The minimum of a quadratic function, a t squared plus bt plus c, occurs at t equals negative b over 2a. This formula will give us the time at which the objects are closest. Then we plug that time back into our distance equation to get the shortest distance. Let's work through an example. This one is from your textbook. Cyclist A has position vector RA and cyclist B has RB. Time t is in seconds. We need to find the shortest distance and when it occurs. First, let's find the vector connecting them, dt. We subtract RA from RB. This gives us 7, 12, 10 to 5 for the initial positions plus t times -3, 5, 5, 6 for the relative velocity. Simplifying this, the vector between them is -5 plus 2t and 15 minus t. Now we'll minimize d squared, which is the magnitude of dt squared. We square the components and add them. This gives us 5 plus 2t squared plus 15t squared. Expanding this out gives us 25 minus 20t plus 4t squared plus 225 minus 30t plus t squared. Combining like terms, we get a quadratic in t. The squared distance, d squared, is 5t squared minus 50t plus 250. Now we find the time t where this quadratic is minimized using the vertex formula. Here, a is 5 and b is 50. So t equals negative of -50 divided by 2 times 5, which is 50 over 10 or 5. This means the cyclists are closest after 5 seconds. Finally, we substitute t equals 5 back into our original distance formula. Plugging in t equals 5, we get the square root of 5 times 5 minus 50 times 5 plus 250. This simplifies to the square root of 125. This is the exact shortest distance. The shortest distance is the square root of 125 meters, which is approximately 11.2 meters, and it occurs at t equals 5 seconds. This quadratic method is robust for finding the minimum distance and the time it occurs. Now let's address our third objective, finding the intersection point of two lines. In 2 dimensions, 2 lines can either be parallel, coincident, meaning they are the exact same line, or they can intersect at a single point. Our method will allow us to distinguish between these cases. If the lines are not parallel, they must intersect. The general strategy is to set the 2 line equations equal to each other. This is possible because at the intersection point, any point on the first line is the same as the point on the second line. Let's say we have 2 lines, L1 and L2, each with its own starting point and direction vector. We are looking for a point that lies on both lines. The key detail here is that we must use a different parameter for each line. I'll use S for the first line and T for the second. This is because the intersection point could be reached at a different parameter value on each line. So we equate the 2 equations, which states that for some value of S and some value of T, the position vectors are the same. This single vector equation leads to a system of scalar equations. For example, in 2D, we get one equation from the x components and another from the y components. We can rearrange this into a standard system of equations with our parameters s and t as the variables. We then solve this system. If the system has a unique solution for s and t, the lines intersect. If the equations are inconsistent, meaning there's no solution for s and t, then the lines do not intersect. If they are consistent but dependent, meaning there are infinitely many solutions, then the lines are coincident. Let's apply this to a 2D example. We will use the example from the textbook. We have 2 lines, L1 and L2, defined by these vector equations. We want to find their intersection point. The first step is to equate the 2 vector equations. We set R1 equal to R2. This gives us R2, 1 plus S times 3, 2 equals 15, 5 plus T times 4, 1. Next, we separate this into 2 scalar equations, one for the x components and one for the y components. From the x components, we get 2 plus 3's equals 15 minus 4t. From the y components, we get 1 plus 2's equals 5 plus t. Now we rearrange these into a standard system of equations for s and t. Our system is 3s plus 4t equals 17 and 2s minus t equals 4. We can solve this using substitution or a calculator. Let's use substitution. From the second equation, t equals 2s minus 4. Substituting this into the first equation, we get 3's plus 4 times 2's minus 4 equals 17. This simplifies to 11s equals 33, so S equals 3. Now we can find TIT equals 2 times 3 minus 4, which is 2. We have found the parameter values SE, LCE, ES, and 3, and T2. This means the lines do intersect. To find the intersection point, we substitute one of these values back into its corresponding line equation. Using line 1 with cell 3, the intersection point is part 2, 1, plus 3 times and 3, 2, which gives us 7, 7. You should always check your answer by substituting T2 into the second line equation, and you'll find it gives the same point, 7, 7. A very important distinction in these problems is the difference between intersecting paths and a collision. This is a key concept that IB often tests. Just because two paths cross doesn't mean the objects will collide. Let's revisit our last example, but now consider the lines as the paths of two objects, say boat A and boat B. So we have the path of boat A and the path of boat B. They represent the trajectory the boats would take if they followed their velocity vectors. To find the intersection of their paths, we set them equal, using a different parameter for each. Equating the paths with parameters TA and TB, we get a system of equations. Solving this system gives us TA equals 3 and TB equals 10. The point of intersection is found by substituting TA3 into boat A's equation, which gives the point 5, 4. This point, 5, 4, is where their paths cross. But did the boats collide? The intersection point is reached by boat A at time TA equals 3 seconds, and by boat B at time TB equals 10 seconds. Since these times are different, the boats arrive at the intersection point at different moments. Therefore, they do not collide. For a collision to occur, two conditions must be met. First, their paths must intersect. Second, they must arrive at the intersection point at the exact same time. So, when solving these problems, always ensure you use different parameters for each object. If and only if the solution provides the same parameter value for both lines, then the objects will collide. Solving for intersections in 3 dimensions is very similar, but with one crucial difference. The process begins the same way by equating the vector equations of the two lines, L1 and L2, each with a different parameter. This gives us our familiar equation, A1 plus SB1 equals A2 plus TB2. The difference is that in 3D, we now have 3 components, x, y, z, not just 2. This means this vector equation gives rise to 3 scalar equations. So we set the x, y, and z components equal, resulting in a system of 3 equations with 2 unknowns, s and t. Solving a system of 3 equations with only 2 variables is different from the 2D case. The process is to first solve 2 of the equations for s and t, and then substitute these values into the third equation. This third equation acts as a consistency check. There are 3 possible outcomes. First, if the third equation is satisfied, the system is consistent, and the lines intersect at a single point. Second, if the third equation is not satisfied, the system is inconsistent, and the lines do not intersect. This occurs when the lines are skew. Skew lines are lines that are not parallel, but do not intersect. They exist in 3 dimensions and never lie on the same plane. The third outcome is that one line is a scalar multiple of the other, which means they are parallel. In that case, either they are also coincident and have infinitely many intersection points, or they are distinct parallel lines and have no intersection points. Let's work through a 3D intersection example to see this consistency check in action. This is the last worked example from your notes. We have line L1 and line L2 in 3D. Our task is to find their intersection point if one exists. First, we equate the 2 vector equations. Setting R1 equal to R2 gives us this equation with parameters s and t. This yields 3 scalar equations. From the x, y, and z components, we get 1 s1 plus 2t, self-1t, and 3 2's 4 plus 3t. We have a system of 3 equations with 2 variables. We must solve 2 of them and check the third. The second equation is already conveniently arranged for substitution. It tells us s equals -1 minus t. Let's substitute this into the first equation. Simplifying this equation, 1 plus 1 plus t equals 1 plus 2t. This simplifies to 2 plus t equals 1 plus 2t, which gives t equals 1. Now we find s using our expression from equation 2. S equals -1 minus 1, which is -2. So, solving equations 1 and 2 gives us SS2 and T1. This is our potential intersection. Now for the crucial part, the consistency check. We must substitute these values into the third unused equation, equation 3. Equation 3 is 3 minus 2's equals 4 plus 3t. Substituting our values, we get 3 minus 2 times -2 equals 4 plus 3 times 1. Let's evaluate both sides of the equation. The left side is 3 plus 4, which is 7. The right side is 4 plus 3, which is also 7. Since 7 equals 7, the equation is satisfied. The system is consistent, and the lines do intersect. To find the intersection point, we can substitute either SO2 into L1 or TO1 into L2. Let's use TO1 and L2. The intersection point is 1, 1, 4, plus 1 times 2, 1, 3, which gives us the point 3, 2, 7. This is where the lines cross in 3D space. Now, let's explore a case where lines in 3D do not intersect and are also not parallel. This is the definition of skew lines. We'll use another example from the notes to illustrate this concept. First, let's write L3 in vector form for consistency. R equals 1, 1, 1 plus U times 2, 2, 4. Before we equate them, let's check if the lines are parallel. We compare their direction vectors. The direction vector for L2 is 2, 1, 3. The direction vector for L3 is 2, 2, 4. They are not scalar multiples of each other, so the lines are not parallel. The vectors 2, 1, 3 and 2, 2, 4 are not parallel. Since they are not parallel, they must either intersect or be skew. Let's find out. We equate the vector equations for L2 and L3 using parameters t and u. This gives us our system of 3 scalar equations. We have 1 plus 2t equals 1 to 2u, 1t equals 1 to 2u, and 4 plus 3t equals 1 4u. Let's rearrange the first 2 equations to solve for t and u. From equation 1, t equals u minus 1. From equation 2, t equals 2u minus 2. Setting these equal, we find that u equals 1. Substituting back, t equals 0. We have a potential intersection at S of 0, UPP 1. Now we perform the consistency check using the third equation. Substitute t as 0 and u to 1 into equation 3. We get 4 plus 0 equals 1 plus 4. This simplifies to 4 equals 5, which is a false statement. The inconsistency of the system means there is no solution, and therefore no intersection point. Since the lines are not parallel and do not intersect, we can conclude with certainty that they are skew lines. This confirms our understanding of 3D geometry. The intersection of lines can also be used to find vertices of geometric shapes like triangles. Let's work through an example where the lines represent the sides of an isosceles triangle. The sides of an isosceles triangle ABC are AB r equals to 0, 2 plus R2, 1. BC RC 8, 6 plus S 1, 2. AC RC 0, 5 plus to 1, 1. Find the coordinates of A, B, and C. The vertices are the intersection points of these lines. We need to find 3 intersection points, A, B, and C. Let's find vertex B first by intersecting lines AB and BC. Setting the equations for AB and BC equal gives us a system for parameters R and S. Solving this system gives R at 3 and S as 2. Now we substitute R3 back into the equation for line AB to find point B. Point B is 0, 2 plus 3 times 2, 1, which is 6, 5. Next, let's find vertex C, the intersection of BC and AC. Equating the equations for BC and AC gives us a system for parameters S and T. Solving this system gives SN3 and TLC2. Substitute SL3 into the equation for line BC. Point C is 8, 6 plus 3 times 1, 2, which is 5, 0. Finally, let's find vertex A, the intersection of AC and AB. Equating the equations for AC and AB gives us a system for parameters T and R. Solving this system gives T53 and R at 53. Substitute T and 53 into the equation for line AC. Point A is 0, 5 plus 5 3 times 1, 1, which is 5 to 3, 10 to 3. We have now found the coordinates of all 3 vertices, A, B, and C. We could now calculate the lengths of the sides to confirm that the triangle is indeed isosceles by finding 2 equal side lengths. You have now seen the fundamental vector applications for point-line distances, object distances, and line intersections. Now it's time to test your understanding with some practice questions. These questions are in the style you might see in an IB exam. Take your time to work through them. Question 1. Find the shortest distance from the point pi EC2 r 3 1 to the line r equals 4 1 3 plus T2 T2 5. Pause the video and try to solve this on your own. Question 2. Two particles, A and B, move according to these position vectors. Find the shortest distance between them and the time at which this occurs. Again, pause the video here. Question 3. Find the intersection point of lines L1 and L2 and confirm whether they collide. Remember to use different parameters. Pause here to work this out. Question 4. In 3 dimensions, determine if lines L1 and L2 intersect, are parallel, or are skew. Pause the video and give this a try. Question 5. A classic application problem. A seal and a shark are in the ocean. Find the velocity vector of the shark, then show that their paths intersect, and finally, find the distance between them when the seal reaches the intersection point. Take your time with these. They cover all the key skills from today's lesson. We'll go through the solutions next. Let's review the solution for question 1. We need the distance from P to the line L. We'll use the dot product method to find the foot of the perpendicular. First, we identify the point A on the line, 4, 1, 3, and the direction vector B, 2, 2, 5. A general point R on the line has coordinates, 4-2t, 1-2t, 3+5t. Next, we find the vector PR. PR equals R minus P, which simplifies to 2 plus t, 2, 2t, 2 plus 5t. The condition for shortest distance is PR is perpendicular to B, so their dot product is 0. Setting PR dot B to 0 gives us this equation. Expanding it and simplifying, we get 33t equals negative 24, so t equals negative 24 over 33, or negative 8 over 11. This is the parameter value for the foot of the perpendicular. Now we substitute this value of t back into PR. This gives us a vector PR with fractional components. Let's find its magnitude. The magnitude of PR is the square root of 46 squared plus 86 squared plus 16 squared, all divided by 33. This simplifies to the square root of 9636 over 33, which is approximately 97 units, so the shortest distance is 947 units. Alternatively, using the cross-product formula, we have AP equals 2 to 4, 3 to 1, 1 to 3, equals each 2, so 2 to 2. APX diab at 2, 14, 18. APXB equals CURT, 4 plus 1, 96 plus 324, equals SQRT, 524. B SQRT, 4 plus 4 plus 25, equals SQRT, 33. Distance EPSD is SQRT, 524, SQRT, 33, which is also approximately 3.99 units. Let's recheck the calculation of t in the first method. It should be tar 1033 based on the notes. In the notes, it was t equals 1510, so my previous example was correct. Let's recalculate the dot product. 2 plus 2t, t, 2, 2t, 2t, 0, 4 plus 4 t's. 4 or 0. This is correct. Plus t has 10 33 is negative 10 over 33. P 33, 86 33, 16 33. BSQRA index 3 say 33. This seems correct. It's worth double-checking all calculations to avoid errors in complex problems like this. Let's look at the solution for question 2. This is a shortest distance between two moving objects problem. We'll use the quadratic method. First, find the vector between them, dt. dt is the position of B minus the position of A, which simplifies to the vector, negative 9 plus 2 to negative 10 minus 6. Now we find the squared distance, d squared. We square the components of dt and add them. Expanding this gives 48 squared plus 156t plus 181. We use the vertex formula t equals negative b over 2a. Here a is 40 and b is 84. So t equals negative a4 divided by 80, which is negative 105 seconds. Since t must be greater than or equal to 0, this means the minimum distance occurs at the start when t0. At t at 0, the distance is the initial distance. The initial squared distance is 181. The shortest distance is the square root of 181, which is approximately 13.46 units. Here's the solution for question 3. This problem involves two objects with their own position vectors, each with a parameter. We need to find if and where their paths intersect and if they collide. First, we equate the two path equations using different parameters, say TA and TB. This vector equation gives us a system of two scalar equations. Solving this system gives TA equals 2 and TB equals 3. My apologies for the error. Let's solve the system correctly. From the second equation, TA is 4 TP HB 12. Substitute into the first. 3 4 TB 12 plus 2 TB equals 20s. 12 TB and 36 plus 2 TB equals 20. 14 TB equals 56. TB equals 4. Then TA equals 4. 12 equals 4. So the correct solution is TA equals 4 and TB equals 4. The fact that we found a solution for TA and TB means the paths intersect. The intersection point is substituting TA equals 4 into the equation for L1 gives us the point, negative 1, 3. Now the all-important collision check. Did they arrive at negative 1, 3 at the same time? Since TA equals 4 and TB also equals 4, the times are identical. This means a collision did occur at the point, negative 1, 3, after 4 seconds. Let's work through the solution for question 4. The question asks us to determine the relationship between two lines in 3D. First, we check for parallelism by looking at the direction vectors. B1 is 2, 1, 1, and B2 is 3, 1, 2. Since they are not scalar multiples of each other, the lines are not parallel. Now we check for intersection. We set the line equations equal, using parameters t and s. Equating the two equations gives us this vector equation. This yields a system of three scalar equations. From the x, y, and z components, we get 2t3s equals 3, t plus equals 1, and t2s equals 2. Let's solve the first two equations. Multiplying the second equation by 2 gives us 2t plus 2s equals 2. Adding this to the first equation eliminates t, leaving s equals 1, so s 1. Substituting back into the second equation, we get about t plus 1 1, so t0. We have a potential intersection at t2 s 1 now for the consistency check using equation 3, substituting t on 0 and s 1 into equation. 3, 0, 2, 1 equals 2. The left side is 2, the right side is 2. It checks out. The lines do intersect. Since the lines are not parallel and they intersect, they are intersecting lines. To find the intersection point, substitute θ0 into L1. The intersection point is 1, 2, 3. Here is the solution for our final question, number 5. Part A asks for the shark's velocity vector. We're given the direction vector, 6i minus 3j minus 2k, and the speed, 14 meters per second. First, we find the unit vector in that direction by dividing by its magnitude. Then we multiply this unit vector by the speed to get the velocity vector, which is 12i minus 6j minus 4k. Part B asks to show their paths intersect. We set the seal's position R1 with parameter T1 equal to the shark's position R2 with parameter T2. This gives us a system of three equations. Solving any two, we find T1 and T2 1. Substituting into the third equation, it is satisfied, which means the paths intersect. The intersection point is for 3, 1, 23. There was a calculation error in my head. The system is inconsistent. Let's solve it properly. From the first equation, T1 equals 3T2. 7. Substitute into the second. 5 3T2, 7, plus 6T2 equals 10. 15T2, 35 plus 6T2 equals 10. 9T2 equals 45. T2 equals 5, then T1 equals 3, 5, and 7 equals 8, so to T1 8 and T2 to 5. Now for the check with the third equation, T1 plus 4 T2 equals the 8 plus 4 5 equals 12. This is consistent. My apologies. The paths do intersect at T1 8 and T2 to 5 at the point to 5 36 30. Part C asks for the distance when the seal passes the intersection point. The seal is at the intersection point when T1 equals 8. At this time, the shark's position is R2 of 8, which is 61, 54, 42. The distance between these 2 points is the square root of 2673, or about 51.7 meters. They did not collide because T1 is not equal to T2. My apologies for the error in calculation during the live example. It is a good lesson to always be meticulous with your algebra. We've now completed a comprehensive review of key vector applications. Let's briefly recap what we've covered. We explored 3 essential types of problems. First, we learned how to find the shortest distance from a point to a line using 2 methods: the dot product for the foot of the perpendicular and the cross product for a direct distance calculation. Second, we developed a method to find the shortest distance and time between 2 moving objects using a quadratic function. Finally, we learned how to find the intersection of lines, whether in 2D or 3D, and how to use the crucial consistency check to distinguish between skew lines and intersecting lines. Understanding the difference between path intersection and actual collision is critical. Always use distinct parameters for each object or line. These skills are fundamental for vector analysis in your IB course. Practice is key to mastering them. If you're looking for more personalized help or deeper understanding of these topics or any other part of the IB, A-Level, or IGCSE curricula, consider contacting DAR Tutors. We offer expert online and home tuition tailored to your needs. Thank you for watching.